So thanks to everybody for coming this afternoon on this sort of muggy, I guess, Friday afternoon. It is my great pleasure to welcome Dr. Tim Barfoot from the University of Toronto's Robotics Institute and UTIUS, I guess, the Institute for Aerospace Studies, to come and speak with us this afternoon. I think many of you already know Tim, or if you don't know him, you know of him. Of course, his research is fairly close, I would say, at least in theme to the stuff that we do in our group, in my group. Okay, the bio. Tim did his undergraduate degree and his PhD at U of T in robotics, and then went off to work for this company, MDA, where Tim and I met, or Tim somehow recruited me. We had met earlier on, I guess, as when I was a PhD student. And we said it at lunch today, sort of that was a pretty pivotal time, I think, for the both of us, where we kind of put together ideas about localization, navigation, control for mobile robots, learned a lot, I think, in the field, and then both of us quit. And Tim went off to U of T, became a prof there, and has had quite a great career. Sabbatical year at Oxford, which was pretty impressive, working with Paul Newman's group. So I think many of you have heard of that group now. Spun off Oxbotica and Oxa, I think it's called now. And then also a leave to work with Apple as director in their, I think it was called the Secret Autonomous Systems Group. So I don't know if you're going to tell us or can ever tell us about anything that happened there. See, there you go. And leads a very impressive, I think, field robotics research group, but also impressive on the algorithm side, I would say. So I think we're going to hear a lot about some really interesting stuff today. It's always a pleasure to hear Tim talk. So please join me in welcoming Tim Barfoot.
Just do a sound check. Is the mic on? Everything's good? Okay. Thanks so much for the wonderful introduction, Josh. It's really, really nice to be here. I'm a big fan of the Ingenuity Labs, and just to prove it, I wore my Ingenuity Labs socks just for today. Yeah, great to be here. So I'm going to talk a little bit about localization and mapping today and some of our recent progress. The title of the talk is Hard Miles, Expanding the Operational Domain for Localization and Mapping. And I just wanted to do a bit of a shout out before I get into the talk that I really think this is the coolest talk poster that anyone has ever generated for one of my talks. So I just wanted to have a shout out to Ramsey there for putting that together. Very, very cool. I'm going to keep that one as an example for our Robotics Institute. So let me just talk a little bit about what our lab does. I mean, Josh kind of explained it a little bit already, but I kind of think of it as we work in two directions. So from the bottom up, we like to create new building blocks for autonomy. So algorithms for localization, mapping, planning, and control. And then we get involved with real world applications. We'll team up with companies, we'll get out into the field and really test the assumptions of our algorithms, deploy them on real robots. These are some of the robots we've deployed on in the past. And I think the secret to a good robotics lab, at least a field robotics lab, is the interaction of these two directions. So being able to go back to the drawing board, come up with new things, try them out in the field, see what assumptions were correct, which ones were wrong, and then head back to the drawing board again. And I think I'll just keep doing this for the rest of my career because I think it's a good operational paradigm. So we worked on lots of different things, but today I want to focus on localization and mapping, and I'm going to talk about 4 different things, which are these 4 columns on this slide. I'll give you a bit of an update on a paradigm that we've been working on actually since Josh and I worked on it back at MDA, called visual teach and repeat, or just teach and repeat when we were doing it, which is a way of navigating a robot along a path. I'll talk a little bit about radar and LiDAR localization on the road for a winter self-driving car project that we have with General Motors. Then I'll talk about something that many of you may not have heard about yet, but a cool new LiDAR sensor that's sort of emerged on the market called Doppler-Lidar, which is, I think, is going to be a game changer for navigation. And then if I have time, I'd like to get a little bit into some of the more theoretical stuff at the end. I'm not going to put up a lot of equations because it's a lazy Friday afternoon, but I'll talk a little bit about these globally optimal algorithms that we've gotten quite interested in, which have to do with the back end of localization. So in a way, like the talk is going from some work on the front end, different sensors, and then some work on the back end of localization and mapping towards the end of the talk. So let's go into the first topic, which is visual teach and repeat. And as Josh said, we worked on the first teach and repeat system together back at our time at MDA. This is actually For those who can't see in the back, that's Director Josh right there. That's me over here. That's our friend Rob Corcoran in the middle. And this was in a mine in Sweden. And this was the first teach and repeat system that we built. Actually, it wasn't on that vehicle, it was on that one, but it quickly became something running on this vehicle here. And you can kind of see this vehicle is navigating itself up and down these mining drifts fully autonomously. And that was actually back in 2005, 2006 timeframe. So a lot of these localization and mapping techniques were actually quite new at the time. And it was, I guess it was a project that was quite timely for us. So we learned a lot. And I kind of fell in love with this idea of having a robot where we could drive it along the paths that we wanted to operate it on and then have it repeat those paths automatically. I'm still fascinated by that when I see the robot do that every time. And in my research group, we kind of took this idea and we expanded on it and tried to do it in other environments. So in the mining environment, we were using 2D laser rangefinders. We started trying to do this outside in more three-dimensional environments using cameras. So this is actually a robot using our stereo visual teach and repeat technique. And basically what it is a framework that lets us navigate using only vision in unstructured environments. The user will demonstrate to the robot all of the paths that it should operate on. So you can imagine this network of 5 kilometers of interconnected paths in an abandoned mine quarry. And then we should be able to command the robot to go to anywhere on that network, and it should plan a path through that network and then repeat by matching its live camera data back to the maps that it's built during the teaching phase. It's pretty efficient in that it only really requires one laptop on the robot to run, one camera, so not a lot of different sensors, and only one training example of each path segment. It's lightweight in that we don't require GPS to do what you're seeing in the video. We don't even really use an IMU. This basic version wasn't even using DNNs. There's no global map, and there's no semantics. So it's about as pared down an example of localization and mapping as you can think of. And it's also composable, meaning we could teach the robot these path segments in one order, and then by putting it together in a graph, we can repeat them in novel combinations that it didn't see during the teach phase. And then finally, by repeating these paths many, many times, it's an interesting vessel for studying lifelong learning problems in robotics. So we can gather lots of data sets by driving along these path segments many times, and then we can use machine learning to improve certain components of our autonomy stack over time. So we've been kind of working on this problem for a long time. I've actually ever since I left MDA and started my faculty job at Toronto. And we've made a little bit of progress on this now. In a bit more detail, under the hood, the way the mapping structure works, and this is quite important, I need to explain this because we'll make use of this later in the talk as well, is that we keep a very relative map structure. So each of these triangles can represent the robot's pose at a certain time. And as the robot's driving, it's observing some landmarks, these round circles. It's estimating its motion, relative motion between two poses using visual odometry by observing features, moving and reobserving them, and then using geometry to figure out its motion. We're also storing the landmarks that we see relative to the first pose at which we saw them. And this allows us to build up a fully relative map structure for the robot. Okay, so under the hood, that's our paradigm. We don't ever try to make this make sense in a global reference frame. Everything is stored relatively. So a bunch of relative transforms and local geometry stored at each pose. And then when it comes time to repeat, what we do is we can just compare features that we've observed from a new pose to the ones that are stored in the map, and then we can work out the transform so we know where we are relative to the path that we taught. We can drive forward. We can still estimate our motion in the live stream of images using visual odometry. So if we don't match to the map, that's fine. And then hopefully a bit later along the path, we'll reobserve some landmark matches and then match and know where we are again. So it's very much a predictor-corrector style of localization. And it's very lightweight, right? We can actually build the map in real time, immediately start repeating on it. We don't need to go away and run a massive offline SLAM algorithm that relaxes everything into a global reference frame. And the nice thing from the control perspective is that because we've got the shape of the path ahead of us, we can actually then use model predictive control to anticipate different things like the lateral curvature, even the vertical curvature. We have examples where there's like a speed bump and we detect that in the teach pass, and then the robot knows to slow down to go over the speed bump as it gets to that point. And so that's actually good enough to do what I showed you in the video on the previous slide. And if you were to zoom into any one of these path segments, it would look just like this under the hood. Everything is relative. Although I'm showing you a picture that looks like it's in a global frame, under the hood, everything is in local coordinates. And we've kind of stuck with that idea in my research group ever since we started doing this. Now, the first thing you're going to realize or think about when you start using cameras outside is that if you build the map at one time, and then you repeat at another time, there could be significant changes in the appearance of the scene. So these are two video sequences 7 hours apart that were taken at the Canadian Space Agency's Mars terrain. To us, they look pretty similar, but to the vision algorithms of 10 years ago, these were a hard thing to match. We were using handcrafted features like SIFT and SURF, and it became pretty difficult to match these things. And so the idea that we happened upon sort of in partnership with the folks at Oxford was the idea of using bridging experiences. So maybe we couldn't match things that were 7 hours apart, but if we had driven the path maybe 3 hours after we'd done the mapping instead of 7, we might be able to match. And so the idea is maybe we can even match things through some bridging experiences. So even if these don't directly match, we can match this to this and then this to this, and then we can know where we are. And if one bridging experience is good, 2 is better, and 4 is even better than that. And we can add as many of these bridging experiences as we like. And so it turns out, even 7 years ago or so, we were able to deal with very drastic lighting and weather change by building up these multi-experience maps. It was actually good enough that we could teach the path or the map, the original map, in broad daylight, and then be driving at night with headlights on. And these things wouldn't match, but by bridging through all of these intermediate things, we could still be driving exactly in our tracks in a totally different scenario. So that was kind of 6, maybe 5 years ago, even we were still doing this. And we've deployed this on a lot of different robots over the years. So here's just a bit of a collage of different robots that we've deployed on. Actually, here's Melissa's work, where we deployed this on the drone that's actually sitting right over there in the lab. You can see all the features that are being tracked. It's doing teach and repeat up in the air. We deployed up in the Arctic on rover platforms. We work with Defense R&D Canada. We deployed on their robot out in the field on the sides of cliffs. And it's just been a good paradigm for us. And I think we'll probably stick with this for a while still. If you're interested, it's actually an open source code base now. So you can download VTNR3. There is a pipeline that works with stereo. There's one that works with LiDAR now, and we're close to releasing one that works with radar. Okay, so that's a bit of a recap on teach and repeat. And now I'm going to talk a little bit about more recent stuff. So although I talked about these bridging experiences and being able to use those to match where we are, the challenge with that is you need to keep driving the route so that you don't let the appearance change too much before you repeat. And then a thing called deep learning happened. And the question arose, well, do we really need these bridging experiences anymore, given the capabilities of deep learning? And I've been a bit of a deep learning skeptic, I would say. I haven't been an early adopter. I'm going to tell you about a project that really convinced me that deep learning does have something to offer in robotics. And so the question was, could we directly match these things without having to use bridging experiences? This is the same place at different times of day. This is at different seasons, all in the same place. And those you would not be able to match with classic computer vision features. And so many people have taken deep learning and tried to apply it to the localization and mapping problem. Some have tried to fully regress pose, 2 images in, pose out. There was the pose network that came out of DeepMind. I'm not a big fan of that. It didn't really get the precision that we needed for teach and repeat. And then there were the people that just tried to learn features. So trying to replace things like SIFT and SURF by deep learning features that would be better at matching across lighting and weather change. And this is just a bit of a non-exhaustive slide talking about some of the folks that did features for matching. The work that I really liked was this one over here called Under the Radar. They weren't actually using cameras, they were using radar. But they were able to learn features that would let them match radar scans. And they did that in a self-supervised way, in the sense that they didn't need to manually label what features would match. They would just use some ground truth for the pose, and then they would use that to learn the features that were needed to produce a good pose match. And so we adopted this idea and tried to apply it to vision. So here's a bit of a crude localization pipeline. We take 2 images that we want to match. We're going to put them through a network that extracts key points, scores, and descriptors. We're then going to build some kind of differentiable matching algorithm that lets us match these features in image space. We're then going to turn those into Euclidean points using a differentiable inverse stereo camera model. And then we're going to run a pose estimator in Euclidean space that will align these features that we've just matched. And at the end, we're going to produce pose. Okay. So the question is, how could we actually train this network in order to do a good job of matching these features? And so by using this under the radar paper idea, the idea was that we would actually only learn this part. We only want to learn these feature descriptors. The rest of this part of the pipeline is actually known. We just build it in a differentiable way. And so what we really need are labels for the relative poses between the images that we can use as a supervisory signal. And for us, the way we did this initially was we took our multi-experience localization, which could actually already solve this problem, and we produced relative pose labels using that older localization system. And then all we had to do was backpropagate through this whole pipeline to try to learn features that would produce the poses that we wanted at the other end. Does that make sense? And so just to talk a little bit about the data that we used for the labels, because we'd built this multi-experience localization algorithm, we could use that to then say, what is the pose of, say, this image with respect to this one? Because we've already localized all of these back to the teach pass, we can work out this transform, and then work out the relative transform between any pair of images in our map that we built. So we could generate lots and lots of training data for this deep learning approach based on this, just to see if it would work. And so in order to train these features, we took some data sets from 2016 that we gathered, one that was got a lot of lighting change in it from the entire daylight cycle, and then another one that was gathered over several months across 3 different seasons. And we generated a bunch of these training labels. Then we trained the features using the pipeline that I talked about on the last slide, and then finally taught some new routes and tried to repeat the routes using these deep learned features. So over here, we see some new areas that we taught some paths in and tried to use these features that we learned. So I just want to distinguish, there was data that was used to learn the features, and then there's the data that was used to teach the new routes. The feature learning data came from 5 years ago. The routes were taught sort of last year and then repeated, but the features were already locked. Okay, so we're not learning features from a specific route, we're learning general features. And it turns out this is actually good enough. You can teach a route in daytime and repeat it at night with headlights on, and you can directly match features between those different experiences using deep learning. And it's precise enough, these features are precise enough that when we work through our localization pipeline, we get good enough localization that we stay exactly in our tracks. No bridging experiences anymore. So these are a bunch of features that are being matched in this nighttime image back to a route that was taught in broad daylight. So these are matches that we're getting between night and day. And those are some of the different lighting experiences that the robot experienced. And a little more quantitatively, this is a graph of time of day and the number of feature matches as a proxy for quality of localization. We taught a route at midday, and we're getting lots of features matched at midday. And we can kind of see that as the lighting is different from the teach pass, we get less features matched. And this is sort of a drop off. This is the sunrise time. There's a drop off here, but it's still plenty of features. That was what you just saw in the video. It's still plenty of features to localize the robot at night, matching back to daytime with no bridging. So for me, that was impressive. That's something we weren't able to do without using deep learning. And the precision of the repeating was all done 100% autonomously, and are using a very precise GPS and post-processing. Our RMSE on the path following was 4 centimeters. So deep learning did something. And a little bit of a longer experiment, we taught a route at midday at the beginning of September, and then kept trying to repeat that route all the way through to the end of November. And this is, again, the number of features that we're getting all the way through over these next 3 months. You can see there's lots of features. Eventually, we get some of these red bars here. Those are places where localization failed for at least 1 frame. So there would be a place where maybe the robot had to be put back on the path. So it's not perfect yet, but it's doing, we would certainly not have been able to do this by any other means than deep learning. And then you might say, well, if I had to build the multi-experience localization system in order to train the features, what's the point? And so in our next experiment that we just presented at ICRA a couple of weeks ago, we actually got away from using the multi-experience localization to provide the labels, and we did this in a fully unsupervised manner. And we did that by sort of 2 steps. I won't get into a lot of the details, but we used a place recognition algorithm to find images that should physically overlap. And then we used an approach called expectation maximization to simultaneously find matches, solve for the poses, and then update the features descriptors. So we're able to do this just completely unsupervised now. Just give it, as long as we have data sets that are roughly along the same path, that start roughly at the start and end in the same place, we can run it through this pipeline, learn features, and then teach a new path and use those features to repeat across large lighting change. So this was kind of surprising for me that this actually worked. So all of that other stuff that we did with multi-experience localization is kind of useless at this point. Okay, so that was the first part of the talk. I'll switch gears now and talk a little bit about radar and LiDAR localization on the road. So as I said, we have a big project working actually with General Motors to do winter self-driving, and my part of that is the localization. And I'll just do a little bit of a plug for my student Keenan Burnett, who put together this really cool data set called the Boreas all-weather driving data set. So we've got, it's really focused on trying to study localization. A lot of the driving data sets that are out there, they have lots of different drives, but very few along the same route. And so if you want to study localization, you kind of want to use some drives to build maps and then other drives to localize against those maps. So you need data sets that are overlapping physically. So we built a data set where we drove the same 10-kilometer route outside of, in the neighborhood outside of our lab. We've got 3 sensing modalities in the data set: camera, LiDAR, and this 360-degree spinning radar from a company called Navtech. There's at least 5 snowstorms in the data, so it really is an all-weather data set. It's over the course of an entire year, so there's changes in the leaves on the trees and all of those things. There's very high quality post-processed ground truth. There's a leaderboard for odometry and localization, and it's hosted on AWS, so feel free to have at it and use some of this data. So we've been using the data to build up 2 pipelines for LiDAR and radar localization. I'm not going to get into the details, except to say that they're very similar to the localization and mapping pipeline that I described for cameras. So we still use one drive to build up the map, and we still use the paradigm of teach and repeat, where we build a bunch of local submaps that we attach along the path. And then we use our live sensor stream to match back to those submaps to know where we are on the road. And this is just a view of the LiDAR and the radar matching back to the map while driving on the road. And the net of it is that we can know where we are on the road with LiDAR to about a 5-centimeter accuracy as measured by post-processed GPS. And with radar, we can know where we are to within about 10 centimeters on the road. And that's good enough for a self-driving car. Industry standard state of the art is probably about 5 centimeters. So radar is not quite as good as LiDAR yet, but we've got some ideas to improve that still. And so I just wanted to make a few observations after having built these 2 pipelines. The first was, you might ask, well, why are we studying radar? Common wisdom is basically that radar will perform better in bad weather than LiDAR would. Kind of makes sense, right? It's at a different frequency that probably is going to be better at seeing through fog and rain and snow and things like that. And so we went into this project thinking what's going to happen is that LiDAR will have better accuracy in good conditions. Radar will be not quite as accurate, but it will continue to be just as good in the bad conditions, whereas LiDAR will fall apart. And that's not what we found. We had a surprising outcome, which is that the LiDAR localization continued to perform at the same level, even in a snowstorm, which was interesting for us. So it's kind of breaking the common wisdom. And there were a few things that are worth thinking about here and why that happens. So one thing is that the radar and the LiDAR do see common structure. So we were actually a little surprised by this. We thought we might see different things in these 2 different sensing modalities, which might not make them easy to match to each other. But they looked similar enough that this actually led to another algorithm, which is try building the map with, say, LiDAR, and then match to it using radar. And that turns out to work reasonably well. But the big surprising thing was that LiDAR actually does pretty well, even in a snowstorm. So here's actually a scan from the LiDAR. And you can see all this clutter in here. This is the LiDAR hitting snowflakes and getting returns off snowflakes as they're falling. But as soon as we run that through our localization algorithm, which has got a lot of different layers of robustness built into it, trimmed ICP is basically the back end that we're using, but it's got robust cost functions. And then later in the pipeline, we've got ransack and things like that. Once you've localized and you look back at which points were not rejected by the localization, all the snowflake points get easily rejected by the algorithm. So there was just enough data. There was plenty of data after you remove the snowflakes to still localize at the same accuracy as when it wasn't snowing. So that was a surprise for us. So I saw there was a paper at ICRA that actually won one of the best papers. And what it was about was trying to remove snowflakes from LiDAR data. And I was sitting there thinking, do we need that? And just in terms of the accuracy, this is a bit of an eye chart, but these are 3 different rows for LiDAR to LiDAR, radar to radar, and radar to LiDAR localization. And this is just backing up my claim at the start to say that our LiDAR to LiDAR is about 5 centimeters accurate on the road. Radar to radar, these are results from this paper. We're actually down to about 10 centimeters accuracy. And radar to LiDAR, we're down to actually about 8 centimeters accuracy. So even better than the numbers that are on this slide. So in a way, this problem is a little bit solved. I think we can localize as well as we need to out on the road. Which makes me think, what am I going to do in the rest of this project? But anyway, I'll turn to the third topic, which I find really exciting. So how many people have heard of a Doppler LiDAR or a 4D LiDAR or a frequency modulated continuous wave LiDAR? All right, good. I'm glad I added this subject matter to the talk then. Let me start by just showing you some data from this sensor. So this is a LiDAR scan. It's mounted on a car. And the colors, you are normally used to looking at a point cloud and the color is like altitude or range or something like that. The color here is radial velocity between the LiDAR sensor and the thing that it's imaging. So right now the car is stopped and you can see these other vehicles, they're moving with respect to us. And so they have a different velocity, a negative velocity because they're coming towards us. Pink means positive velocity because it's moving away from us. And now once we start to move, we now have a relative velocity with respect to the scene. And so everything is changing colors at this point. So immediately you can start to think, wow, I can already start to do like free segmentation of moving dynamic objects. That's going to make perception easier, right? We're working with a company called Aeva that builds this Doppler LiDAR. There are a couple of companies that have brought these to market in the last couple of years. Another one is Blackmore. I don't know too much about Blackmore's LiDAR, but we've been working with Aeva for about a year on this. They've been working on the perception side of things. So the thing that we've been working on is trying to see if we can just do LiDAR odometry. What advantage does this extra velocity information bring in terms of trying to improve our LiDAR odometry? And there's a few advantages, it turns out, but let me just tell you a little bit about how this sensor actually works. So the ranging principle is based on frequency modulated continuous wave. And what that basically means is that, so normally in a LiDAR, you send out a chirp and you sort of time how long it takes to come back. And from dividing by the speed of light, you end up with the range, right? In frequency modulated continuous wave, you actually send a frequency modulated chirp. So as time goes on, you're sending a chirp that gets faster and faster in frequency. It then reflects off the target, comes back, and there's a shift in the frequency spectrum of the return signal. And by measuring that frequency shift and knowing the slope of this modulation that you chose, you can use this formula to work out the range to the object. Great. It's actually even more robust than standard time of flight. The challenge is, though, if things are moving relative to one another, there's actually another frequency shift that happens because of the Doppler effect. So now you have 2 delta Fs. You have one from the fact that there's a range and another because there's a relative velocity. And so to disambiguate those, what you can do is you can send out a second chirp with a negative slope. When you send out the chirp with the negative slope, the range delta F changes sign, but the Doppler delta F does not change sign. So then you have two equations and two unknowns, and you can solve for these two delta Fs, and therefore you have both range and velocity to the targets for every point in your scan, which is pretty cool. And it's only radial though, right? So just have to bear that in mind. That's got some implications for what we can do with the data. So what are some advantages of this? Here I'm showing Velodyne LiDAR, standard time of flight in a snowstorm. And in a minute, it's going to switch to this Doppler LiDAR. So now this is the Doppler LiDAR, same snowstorm. Actually, the data were gathered simultaneously. And you can see all the snowflakes are automatically filtered away at the hardware level. And it's because when you build that system of two equations and two unknowns, the first chirp hits the snowflake, and the second one probably does not hit the snowflake. So the solution to your two equations and two unknowns doesn't make sense, and you can easily invalidate that data point right at the hardware level, which is pretty neat. We, of course, get this velocity information, so we can do things like identify dynamic objects very easily. And as we'll see when we start to do lidar odometry, it turns out that the advantage is that we can start to do odometry even in geometrically degenerate situations. And so the obvious one is a long tunnel. Normally, when you're taking lidar scans and trying to estimate your motion, there's a gauge freedom along a tunnel, because when you match the scans, you get the same cost, even if you slide them along each other. So we decided to build a lidar odometry algorithm based on this Doppler LiDAR. It's a bit of a busy slide again, but let me walk you through it. What we're doing is we're taking LiDAR scans. We're accounting for the fact that they're motion distorted. So every point is gathered at a different pose of the LiDAR because you're moving while scanning. We're building a map. We're matching all of the range information back to the map. We also have a motion prior that says our velocity, barring everything else, we'd like our velocity to be constant. And then we have this extra velocity information for every point. And so by putting all of that information together into a cost function that we want to optimize, it looks something like this. We then solve for the optimal pose change that will minimize this cost using all of this information together. So it's basically the same as a standard odometry algorithm, except for the green dots, which are new because they come from the velocity information. We put the LiDAR on our car, Boreas. We gathered some data sets. We also augmented that with some data sets from our partner, Aeva, who gathered data in some very long tunnels in the US. And then we evaluated the algorithms. And we compared to a few other baselines. Again, a lot of data. This is some data from tunnels, and we can see our algorithm is actually doing quite a bit better on the error metrics in long tunnels because we're able to get our motion in the longitudinal direction down the tunnels. But even on highways, we tend to do a bit better than the other algorithms because there's even some degeneracy of geometry when you're out on the highway and there's not a lot of obvious building structure. And at higher speeds, the benefits actually get better for us with the Doppler information. And then even when we range limit our sensor data, we can really see that our algorithm does better. So it does seem like it doesn't actually cost a lot of extra to add this into the pipeline, but it lets you solve some edge and corner cases that you wouldn't be able to otherwise. Here's an example just in a tunnel. So this is a 300-meter long tunnel. And by not using the velocity information, actually even our algorithm ends up foreshortening the estimate of the length of the tunnel by about 100 meters. But once you have the velocity information in there, we're matched very close to the ground truth, even at the end of the tunnel. And here's again, just the data and our odometry algorithm operating on the data. We've got ground truth in red and our algorithm in blue. And I can kind of skip forward, but even after about 8 kilometers of driving, we're still very, very close to the ground truth. Qualitatively, it looks good. And then the other thing we thought once we'd built that first algorithm was, could we actually do something even simpler? Could we get away from having to do ICP at all? Do we really need to match points back to the map? Do we need correspondences? Because we've got this velocity information, you can kind of imagine like an optical mouse, right? When you run an optical mouse on the table, you're not really doing correspondences. You're just looking at the velocity or the flow of the changes in the intensity of this downward-looking camera to kind of estimate motion. And so we decided to see if we could build a correspondence-free LiDAR odometry algorithm, which would run really, really fast, because that's the slowest part of LiDAR odometry. And it turns out that in theory, you can actually take all of this velocity information and turn it into velocity of the LiDAR itself in 6 degrees of freedom, but only if you have at least 3 of these LiDARs that are not located in a line. If you only have 1 LiDAR, you're actually degenerate by 3 degrees of freedom. And it's because you're only getting the radial velocity. So we algebraically showed that was the case. Unfortunately, we only had 1 LiDAR. We're working on an experiment right now to get the company, actually I have a student down in Silicon Valley right now doing the 3 LiDAR experiment. But at the time, we only had 1 LiDAR. So we actually put a 3-axis rate gyro co-located with the LiDAR so that we could pick up the 3 degrees of freedom that we can't measure with the LiDAR. We then turned all of that into 6 degree of freedom velocity of the LiDAR itself. And then we just integrate that for pose. It runs super fast. It's correspondence free. It's 5 milliseconds update per LiDAR scan. It's not as good as ICP, but it's super fast. And I'll just show you a plot of how well it's doing. So black is ground truth, I think, yep. And green is this new super fast LiDAR odometry algorithm, whereas orange is the slower, more expensive one that does correspondences. So it's not terrible. And it's probably actually good enough that you could run this for 100 meters and then do like an iterative closest point update back to a map in order to know where you are. So that's like a nice compromise. And it's something, we often think as roboticists that we need to improve the algorithms, where this is an example of improving the hardware and using physics to solve the problem rather than deep learning. So I'm not just a deep learning advocate today. Physics is also good. So let me come back to do I have time for the last section of the talk? I'm good? Okay, great. So I've talked a lot about the front end, different sensors. Now I want to talk about a topic that I find really, really exciting. I like to keep a first author paper in my files that I'm working on at all times. And so this is where I'm kind of spending my own research time at the moment. And it's this idea of globally optimal algorithms. So whenever we set up one of these optimization or localization or even model predictive control kind of problems, we're always setting that up as an optimization problem, right? How many people have set up their algorithm that they're working on as an optimization? I'm going to say it should be almost all of you raising your hands. Okay, almost everything is an optimization algorithm. And usually it turns into some kind of nonlinear least squares problem. And the nonlinearity comes from the fact that we have a nonlinear sensor model or a nonlinear robot model. And then we build these squared error terms, sum them up, and then try to minimize that. And we're typically satisfied by finding some local minimum of that cost function because it's not a convex cost. Okay? If it were a convex cost, it would have one global minimum and we could find it and we would know we were at the minimum. But our costs are never convex. They're always non-convex, which means they enjoy local minima. And if you initialize your algorithm poorly, you can find yourself trapped in a bad local minimum. And the question is, how do you know that you're in a bad local minimum? Usually we don't, right? We just give up and we try to reinitialize. We guess that we're in a bad local minimum. We try to reinitialize at some other point. And if the cost gets lower, we're like, aha, that must be the global minimum now. But there might be another global minimum that's even better than that second one, right? So how can you actually guarantee this? And for a long time, I would say in robotics, we didn't think that was possible. We thought we would just have to make do with that. And so this last part of the research is, it turns out that there are techniques that we can borrow from optimization theory and mathematics that say that we can say something about whether we're at a global minimum or not for some problems. And you have to do a bit of work to get your problem set up as one of those problems. And I'm just going to walk you through, this is the mathiest part of the talk. I won't get too mathy. I'll try to give you the intuition for what's going on here. So there's some math, but let me just walk you through this. So we start with one of these non-convex optimization problems that we've set up. We've just got some f of theta. We don't know anything about f, right? There's no structure to it other than that it's nonlinear least squares. And we want to find the minimum. Obviously, we're going to get stuck in a local minimum. The trick is we want to take this problem and convert it into another non-convex problem called a quadratically constrained quadratic program. And all that means is that the cost that we're minimizing is quadratic, but it comes along with quadratic constraints as well. And we can do that by taking these theta parameters and doing a nonlinear, we have like a cleverly chosen nonlinear transformation on them, so that this becomes a quadratic cost in some new variables x that are a function of the original variables theta. And then typically these constraints come from the fact that we've had to introduce extra variables in order to make that cost become quadratic. Okay, so often we can do this. This part is not actually that hard. There's a little bit of seeing a few examples of how other people have done this on other problems. You can look at a new problem and do this pretty quickly, it turns out. The problem is this is still non-convex, but now it has a very specific structure because it's one of these QC-QPs. The next step is we reformulate that problem. If I were to not cross out this thing in red, I can exactly reformulate that problem using identical math over here by just sort of using the trick that the trace of x transpose is x transpose x. Everyone should remember that from linear algebra. So I can manipulate that into here. And then what I do is it turns out you need to then have you're going to define this big X to be little x transpose from over here. Then this problem is the same as that, except that this rank 1 constraint appears. And what we're going to do is we're just going to quietly forget about this rank 1 constraint for a moment. Once we do that, once that's gone, this problem is actually now convex. Simply by dropping this rank 1 constraint, we now have what's called a convex relaxation of this problem. Because it's convex, it means that there's only one minimum. And so in theory, we can solve this problem in polynomial time using some algorithm. As stated, this is actually called a semi-definite program. And there are many existing solvers out there for semi-definite programs that you can download and use. So that's like a well-researched area in optimization. There's some tractability issues still, but you can actually do it. And so the key thing is, if I take this convex relaxation where I've dropped this rank 1 condition and I solve it, and the big X happens to be rank 1 after I've solved it, it means I've actually solved the original problem. And I know that I'm at the global minimum of the original problem. So let me just say that again. The convex relaxation is the same as the original problem minus this rank 1 constraint. I'm going to solve that convex relaxation. If it happens to be rank 1 at the end, once I get my solution, I've solved the original problem. I now know I am at the global minimum of a non-convex problem. So there's a bit of a leap of faith there. The question is it going to be rank 1 in practice? And it turns out for a lot of problems that we care about, with the right setup, that magical set of conditions happens. We solve the convex relaxation and the solution becomes rank 1. And therefore, we know that we're at the global minimum of the original problem. It's a little surprising. It sounds like magic. In theory, you can't solve a non-convex problem in polynomial time. And now somehow we are. But the only thing that we're giving up is that we can't guarantee the solution will be rank 1. We just have to be happy that it turns out to be, in practice, rank 1. I could say other things about this slide, but that's really the nutshell of what's important there. So can we take these ideas and apply them in robotics to say something about the global optimality of our algorithms? And it turns out that lots of people have actually been looking at this quietly in the background, both in computer vision and in robotics. And so I think there's like 4 main groups of algorithms that now have globally optimal algorithms associated with them. So one of them is just rotation averaging. I've got a bunch of different noisy estimates of rotation, and I want to average those. You can get a global optimality certificate for that. Pose graph optimization, this amazing work. If anyone has not read the SE Sync paper by Dave Rosen et al., it's really amazing. Large scale pose graph optimization, which is like SLAM, but without landmarks. Globally optimal algorithms. Point cloud alignment, this amazing work by Luca Carlone at MIT. You want to do point cloud alignment, only you have a whole lot of outliers, maybe like an outlier rate of 90% or more. You can pose this using a robust cost function as a non-convex optimization. They use the tricks that I just told you about to show that they can find the global minimum even with robust cost functions involved. So very robust point cloud alignment with global guarantees. And then finally, some work even from my own department, from John Kelly's lab, where they were doing extrinsic calibration of different sensors, and they were able to show that they could get global guarantees on those minimization problems. So it's very exciting, and we sort of dove into this over the last couple of years, and we have a couple of papers, slide is not advancing, a couple of papers coming out at IROS that are already out on RAL. And the first one is we looked at the range-only localization problem. So you can imagine you're in a warehouse with a bunch of ultra-wideband anchors, and you're roaming around, and you're just getting ranges back to a roving receiver. And you want to solve for your position, not pose, just position. This turns out to have local minima. Here's an example of a local minimum solution from one of these problems. And we were able to derive a global optimality certificate for this problem. So we can say that this solution is global and this one is not. And then a related problem to SE-Sync. So SE-Sync was pose graph optimization. They didn't have landmarks. So we were able to extend SE-Sync to include landmarks. So now, like classic landmark-based SLAM, we derived a very, efficient optimality certificate for classic SLAM. And so we can tell the difference between this bad local minimum and this correct global minimum using these techniques. Here's some other examples of local minima. So like you've got robot driving in a circle, it comes back and gets a loop closure. You can actually get these weird contorted local minima. It's like if you've ever got one of those green screens from the pandemic age, where you put it behind you for Zoom, and you try to fold those things up and put them into the bag. They have these metal hoops. There's sort of like, once you fold it up to put it in the bag, it's at a local energy minimum. That's what these solutions are kind of like. And of course, the global minimum is when the whole screen pops open. So we're very excited about this, but there's a gap still between the problems that we can apply these techniques to and those, deployed algorithms out on the road, right? These are highly simplified problems compared to once you start putting RANSAC into the problem, all the global or robust cost functions into the problem and all that. So there's still some work to make it super practical, but I'm very excited about it. And just some other things as I start to wrap up that I didn't get to really fit into the theme of localization. We have been deploying teach and repeat out in the snow a little bit with our partners in the military. So this is a fun field test that we did with the Canadian Forces. This is LiDAR teach and repeat operating in the winter on a tracked vehicle. One thing that's been on my to-do list for a long time with teach and repeat is to incorporate local obstacle avoidance into teach and repeat. So we actually took John Gamel's FitStar algorithm and applied it as a local planning algorithm to avoid obstacles. And the idea is you want to stay close to this taught path, but still avoid obstacles. And we come up with a nice trick for doing that. In a collaboration with Apple, we've been looking at operating in cluttered indoor environments with lots of people walking around and trying to use deep learning to build prediction models of how humans will wander in an environment. So I give you 3 historical LiDAR scans. The network should tell me what's going to happen for the next 10 scans, and then we can put that into planning to anticipate where people will be and avoid them. I've done quite a bit of work on state estimation. If anyone has cracked open my book, there's a second edition that's now available on my webpage, which should be out next year from the publisher. And we've been applying some of those ideas with some new collaborations in the medical world, where instead of doing mobile robot trajectory estimation, we're doing continuum robot shape estimation with very similar tools that we use in mobile robotics. And I'm just going to stop there. I got to do all the talking, of course. All of these folks did all of the hard work, and thanks to all of those folks for funding it. Thanks very much for your attention.